Afternoon, everyone. In today's presentation, they will take you through my audiobook generation technology. Over the past few months, my team has been dedicated to developing a text-to-speech generation model that uses advanced machine learning technology, the details of which will be shortly explained. My colleague will now kick off with a short introduction. Please take your seats and enjoy the presentation.
Okay, hi everyone. So as our model just told you, our project is about text-to-speech for audiobooks. My name is Alaa Alkady, and with the supervision of Dr. Mohamed Shalan, and joined with me are Linah, Mohamed, Ibrahim, Salma, and Fady. So before actually telling you about the project and everything, I'm just going to tell you what we're going to talk about. So, so we're going to tell you about why we chose the project in the first place, our process through it all, and the future prospects that we think are going to happen. So you might think that text-to-speech is done everywhere. So why are we actually doing it again? Well, there's statistics that show that there's a 113% increase in people actually wanting to listen to audiobooks. So they'd rather listen to the book while they're driving their car or before they sleep, rather than they'd actually read the book. So not only that, but we decided, because we all have a shared common interest to knowing machine learning techniques, we had to do this project. So our objective of it all is we want to help users, because we wanted to help them to listen to the book at their own convenience. And we're also helping them because we're helping the people that read the book for hours and hours to just put one book on Audible. So our main objective is to create a text-to-speech model to have as natural sounding, to be as natural sounding as possible. So Salma is going to tell you about the technicality of it all.
So our main usage model is a concatenation of Tacotron 2 and WaveGlow, providing an end-to-end speech synthesis solution to the problem Alaa mentioned earlier on. During the research phase of our project, we chose this model because it had a higher MOS score than a substantial amount of those able to generate text-to-speech. And it was reviewed in the literature as having one of the most natural sounding outputs. Tacotron 2 is responsible for taking the input text and generating the MEL spectrogram, which is an is a visual representation of the audio waveform. And then WaveGlow takes the MEL spectrogram and generates the final audio waveform as the output. The model uses an attention mechanism as well, which in very simple terms is what decides which pieces of information that should be further emphasized in order to make the output more expressive and as human-like as possible. The model was already pre-trained on the LJ speech dataset after it was open sourced by NVIDIA, which contains 24 hours of audio data from a single American accent female speaker. Another data set we used was Libby speech, which contained multiple speakers with different accents and varying styles. This data set is much larger and has about 1,000 hours of audio data. Having the model being pre-trained on the LJ speech dataset provided us with a clear foundation for articulate speech synthesis and allowed us to explore training on both paths, using LJ speech for further training and the other using DB speech, in order to ultimately decide which would provide us with the better output.
Now let me show you the progressive journey of our TTS generator. Let's dive into the first stage.
Thing off. I couldn't put my finger on what exactly it was, but it was definitely fair use. Something was out of balance. I decided as I stepped off the bus and onto the sidewalk outside John F. Kennedy Prep. The place looked like it did almost every other day.
So, as you may have noticed, there were plenty of challenges. Pronunciation was off, sound quality was subpar, and there were random pauses and glitches. Not to mention, the output of the model was limited to a mere 10 seconds before turning into complete chaos. So we started tackling the problem from different angles. We refined our dataset, we tweaked our model, we upgraded our GPU, and we started experimenting with various epochs. As we progressed, the second iteration emerged. The result was better, but it was still lacking. Let's hear it out.
There was something off. I couldn't put my finger on what exactly it was, but it was definitely there. Something was out of balance, I decided, as I stepped off the bus and onto the sidewalk outside John Kennedy Prep. The place looked like it did almost every other day.
So as you can identify, the output improved a little bit. Sound became richer and the pronunciation progressed. However, critical issues persisted. You could still hear pauses in the sentences, and the intonation and stress were just unacceptable. And this is a big problem. Imagine, for example, our generator producing a sentence that should be said as, I didn't steal your food, in saying it like, I didn't steal your food. This could totally mislead the listener. So our journey didn't stop there. The third and final stage arrived. Pronunciation progressed and was refined. Intonation improved. And not only that, but the output length changed from having a limit of 10 seconds to being any desired length. Let's hear it out.
There was something off. I couldn't put my finger on what exactly it was, but it was definitely there. Yes, something was out of balance, I decided as I stepped off the bus and onto the sidewalk outside John F. Kennedy Prep. The place looked like it did almost every other day, with its red bricks, bright colored banners strung up everywhere, and the jumble of students lingering around outside the front doors. The school had been around for more than a century, and it had that old New York feel. Nothing was ever out of the ordinary, yet the gray clouds rolling in across the sky felt smothering, bringing with them a feeling of suspicion and sadness.
So this is a demo of our web app. As you can see, it has full functionality. You just input the text and get the output audio. So from struggling with pronunciation and sound quality to the possibility of achieving long lengths of high quality audio, our TTS solution has come a long way. Now I'm going to let my colleague Fady show you how we did this transition. Thank you.
Okay, so this is the final design of our text-to-speech model. We first start by inputting the entire book to our text segmentation algorithm, which by doing that, it segments the text into manageable tokens of up to 380 characters. These small tokens are easy to manage by our model due to the constraints of our GPU power and resources. This ensured that the model always stayed stable and also efficient in generating the audio files, as you saw in the demo. These text segments are then passed to Tacotron to generate the MEL spectrograms, as my colleagues mentioned, and then the MEL spectrograms are passed to WaveGlow to generate the audio files for each small text segmentation, and then it passed to the audio concatenation algorithm to stitch the audio files together to actually generate the audio file. It's clear to mention that the text segmentation doesn't just segment the text anywhere. It makes it smoothly so that it doesn't cut sentences in the middle, so that it doesn't suddenly change the context for the Tacotron model. And by doing so, we actually trained the Tacotron 2 and WaveGlow models on the Libre speech dataset to actually have a good one speaker identity, as you heard in the audio file, in the demo. And then we trained on the Libre speech dataset, as it contains small sized audio files from actual audiobooks, which made the model easier to actually understand and have a natural sounding narration voice. After doing so, we actually tried to embed more extreme emotions and depth in emotions in the text. So to do so, we actually passed each text segment to our BERT classifier, which classifies each small token with the emotion that should be imposed on the file. And then these text labels with the audio files generated from WaveGlow are first passed to the CWT and F0 model. This model uses cycle GANs also, and we chose this model because it had two main approaches. The first is that it could change an audio file from a normal, natural sounding speaker to an actual emotion that we want to impose on it based on the label text. And it could also change the speaker identity if we trained it on a different speaker, which we wanted to use in a future iteration of our project. However, the model itself was very unstable and we couldn't get it to work. So we changed and started using the EMOM unit model, which proved to be a better model as it had the best mean opinion score for the 5 models that we were testing. And it also had remarkable outcomes in actually maintaining the speaker identity so that all text segments have the same speaker without changing them. And now my colleagues will say why we didn't actually implement the EMOM unit model in our final project design, as the audio output actually had the emotion that we intended to put. However, the audio quality itself degraded, so actually made the user experience lesser than actually having the tachotron by itself.
Okay, so as Fady just mentioned, the model that we decided to go forth with is the MUM unit model. We used it for 3 main reasons. The first one is because it has unparalleled data. So this helps us because we care mainly about the tone, the pitch of the actual sound. We don't really care to have the sound, like the same words from one audio to the other. So that's the first reason. The second one is using cycle GANs, which has 2 discriminators and 2 generators. So the generator generates audio, fake audio, and then the discriminator analyzes said audio and checks if it's correct or not. And then the last reason is because it aligns with our project outcome and also with the data set that we're going to use or that we used in general. And Mohamed's going to tell you more about that.
Okay, so we trained our model on the EMOCAP dataset. This dataset contains 12 hours of rich audiovisual data. It features 10 professional US English speakers, 5 of which are males and 5 of which are females. This 12 hours is divided into 5 sessions, and each session is a unique neutral dialogue between a pair of speakers with different emotions like sadness, happiness, anger, and neutral. This diverse set of emotions is key for training our model to be able to recognize and generate various emotional tones accurately. We also customize the data set for our own specific needs. We splitted the data set into different or multiple subsets for each speaker and for each emotion. This approach helps us in maintaining the speaker unique identity while converting from one emotion to another. So as you can see, for each emotion, there is a source subset and there's a target subset. The source subset contains of 100 sentences for training and 32 sentences for evaluation or validation, while the target subset contains 128 sentences for training and 43 sentences for evaluation. And now we will be demonstrating our emotion conversion model with 2 recordings. The first recording is the neutral audio or the original audio with a neutral emotion, and the other audio is the generated audio with an angry emotion.
Pennies always get you because then you end up spending like, 50 bucks. But the pennies always get you because then you end up spending like, 50 bucks.
Okay, so as you all heard, there's a variation in the pitch, the volume, the tempo, and the tone, which are the prosodic aspects that mainly convey any emotion in general. However, as Fady mentioned, that the quality is not as good as we intended. So we thought we believe that we don't integrate this model into our final product, as it does not align with our main objective, which is having a natural output sound. And now Linah will be discussing more about our project empowerment.
But the pennies always get you. But the pennies always get you because then you end up spending like, 50 bucks.
Okay, so our project empowerment outcome was centered on providing high audio quality using the text-to-speech synthesis technology. We wanted to establish this initiative as a community deployment project, just so we would make it freely accessible for the AUC community. Sorry. Okay. Okay, we take great pride in showcasing the demonstrated audio that you heard in our presentation, all which is achieved with our constraints of limited resources. And in comparison with other TTS technologies, our exploration led us to 11 labs. 11 Labs is a notable newcomer in the field, and it has an exceptional voice with embedded emotions. However, when looking to their pricing plans, it raises some concerns. Here, the first pricing plan, it says that reading one book costs you $100, and opting to the creator plan will cost you even more. It will cost you around $142. So just to illustrate, in 27 days, the book that we used is around 458,000 characters. So while it may take some time to generate the whole book with our current resources, but it becomes apparent with the cost effectiveness of our project when compared to the pricing of 11 labs. Finally, our project empowerment outcome is undeniably satisfied by expanding the TTS technologies of audiobooks by making it accessible, inclusive, and freely to all the AUC community. Thank you.